Alright, time for another adventure in science with Draft Physics. Yeah. Alright, try something different. Anyway, okay, just a little current events kind of news. Apparently my physicist, who agreed, is now unagreeing or something. He's not answering my emails. Last thing I heard from him was, I'm going to do some research on this photon stuff. So he was be prepared and, gone. So I went out pursuing, with new hope, just endeavor to persevere. So I'm having this really funny conversation with Baldy Cats. I mean, funny in the sense that just everything, you just can't communicate with human beings. It's just impossible. I don't know why I've been doing this all this time, because it's just not possible. You can speak perfectly sensible sentences and get gibberish back. Anyway, so, I mean, it's a little bit rude to ask publicly, but what the fuck? This, none of this should be cabal-y, secret kind of crap. This isn't the kind of stuff you gotta hide from everybody else. It's not like having a little penis or something. No reason to hide. Anyway, how much would I have to pay you per hour for the opportunity to publicly interrogate the credibility of your physics truth? See, this is one of the characters who does, like, the Thunderfoot thing. Let's go find somebody saying something stupid and make fun of them. Yeah. And, especially, I mean, the video was titled something preposterous, like, the worst pile of crap ever spoken on the internet. The most dangerous misinformation on YouTube right now. Well, I guess he added the right now. Obviously, what's always the most dangerous is religion. Okay, that's always got to be the first on the list of the most dangerous to anything called rational cognition. You want to turn a brain into fucking anal tissue? Yeah, believe in a god. There, you've become a menace. But, so this guy's arguing there's no viruses. I don't know whether he's arguing there's no diseases, so maybe he's blaming something called a virus or a nirus or a virus. What's the difference? I mean, obviously you can't deny people are getting sick by being associated with each other. Duh. Yeah, I mean, nobody could deny that, could they? Well, anyway. But he wastes the whole video on, trivia about viruses, trivia about what the standards are for how many have to show up in the, growth cellular culture or something. Whatever. Who cares your standards, whether it's tall enough to be a real virus? Anyway, I mean, okay, I'm taking shots I don't need to take. Fine, yes, we all have to be terrified of viruses. I'm not even saying, look, there's reasonableness, okay? Slow the thing down so not as many people get sick at once, but yeah, we have to admit that, 60% of the population has to get it within the next, 14 months, before it becomes benign, evolves into just a cold. So I asked him that question, and what's the answer? $600. I'm saying, well, that's a little bit high, isn't it? I mean, you're not Barbara Streisand or something. What the fuck, $600? So then I ask, if it's not too difficult to question, what other work do you get $600 an hour to do? And frankly, look, there's two ways we could do this. I would like to just do it as, okay, you just take an hour and you answer the questions as the common physicist with your common amount of knowledge. Now, it would be nice if you could actually research a little bit, maybe watch a couple of my videos and then try to explain what the fuck I've gotten wrong. That might be useful. And, that would obviously take more of your time, and so it'd be a good reason for you to get compensated for having to take a half a day of your life or something to know what the fuck I'm talking about. But frankly, I can just interrogate your physics. I can just find out how much you know about the experiments and what was actually conducted and what wasn't conducted, and what's, what experiments you're telling me what electrons do based on what silver atoms do and that kind of crap. Do you know that a beam splitter isn't 50-50 silver? That it can't be 50-50 because the surface of the glass reflects some light? Yeah. Do you know those little things? Anyway, can't be two equal beams. Do you know that? Or do you not know that? I'd like to ask you all these questions and see how much you really frickin' know about what your elemental science has proven. You know, what is the dark matter but the most preposterous, invisible man, scapegoaty, vacuous, silly answer in the history of mankind? I mean, you're asked a question, you know, how did it happen? Well, the invisible dark matter that doesn't have any regular matter properties must be doing it. The thing you can't see it, it's not of the stuff we're made out of, and so it's totally disconnected from any evidence. You know, I mean, it's like the stupidest answer to the question. You talk about Dunn and Kreger, you talk about all this bullshit. I mean, isn't that like the biggest con artist kind of crapola? Like you're just pulling the wool over the dumbass's eyes by coming up with an answer that fucking silly, and they fell for it. Holy shit. Yeah, I'd like to ask you that question. Don't you think that's a silly place for science to go? Is to start inventing deliberately unfalsifiable invisible man stories? Ugh, pathetic. Anyway. So then he says, okay, 700. Oh no, I said, now maybe it's that difficult to defend the standard woo. Yeah. So he says, okay, 700. Oh, that sucks. Then he says, make me an offer. Well, okay, I'd like to do that, but, you know, frankly, I'll offer you 10. You say, oh, no, 500. You know, whatever. 15, 450. You know, we could do that back and forth, but I don't know if that's really a great idea. And so I point out, I'd really like to fairly compensate you for your time. I mean, I really sincerely want to be fair. I mean, you don't have any interest, you know, just by me asking. I mean, I did ask in the past. We have conversed before in comment sections. I mean, I have politely asked, could you give a shit? Give me some of your time? And you didn't give it away, so you weren't interested. You weren't interested and then not interested, let's put it that way. So, yeah, so I'd like to be fair about it. I mean, you make money doing this YouTube crap. I mean, clearly your videos take a lot more time than the time that they're on display. Okay, so you can't say like, well, 30 minutes of my video takes, you know, 600 hours of production time, so therefore I'm getting such and such a price, you know. I mean, I wanted a fair price, you know, the price over the whole production of a video. How many hours it takes to make, you know, whatever you're getting for your video work. I'm willing to pay that, plus a little bit more. All right, anyway. So then I say, well, I would really like to fairly compensate you for your time, but don't want to be much poorer to do so. See, I already am poor, and I have to become poorer to do this, which really sucks. Would also be interested in how much you would charge if the video was posted on your channel. I mean, it's the real... That would be the real advantage. I mean, he gets, you know, 40, 50,000 views on videos and stuff. You know, this would be to my advantage for sure. I'm willing to pay 3 digits for that. Yeah. And then he says, right, which is just totally unhelpful. Whatever it is, I don't know whether it's sarcasm or whether this is really what he's saying. Don't be bloody daft. I don't charge money for my time. And then a laughy cry face. What does that mean? How is that a useful response to my statement? I mean, I can't go anywhere with that. That doesn't tell me anything. It doesn't give me any new information. Obviously, you do charge for your time. Or, I mean, obviously, you don't give your time away where I think you should. Like, to something that's actually a challenge, not like beating up retards. So, I mean, I'm just asking you, you know, if I pay you, will you fight somebody who's not a retard? You know, can I bribe you into fighting somebody a little taller than 2.5 inches? You know, can you kick the shit out of something other that's already shit? You know, can you kick something into shit? Can I see you do that? Take something that's got some integrity and beat it to crap? That's the kind of fight I'd like to pay to see. And I don't see you doing that, so that's all. I'm just asking to take on, you know, a little bit more of a challenge. Yeah. So anyway, something that picks at your little gingerbread house and see how many cookie crumbles it can, you know, withstand. How much pressure can it take without it falling apart? Anyway. So that's the progress. I mean, I've been there and done this. I mean, like I said, it's for 4 years or whatever it is now. I've been trying to solicit this conversation. And, you know, they all talk like, oh, yeah, it's really open science, blah, 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 blah. Right, I've been banned at every forum. I've posted a polite comment about a discussion about the elemental conclusions drawn by physics. And in, you know, 43 minutes or less, my post is deleted and I'm banned. So, I mean, yeah, there's no open willingness to have this conversation. I have to, you know, clearly, I have to bribe them into it, and I'm trying to humiliate them into it. I'm trying to do all kinds of things to get them into it, but I can't get anybody to show up. And again, I got another physicist who dropped out on me. I mean, it's just, you know, it's just such. Clearly, you know, you guys have nothing to gain when, you know, somebody's throwing rocks at your house for a change. You know, but if you're going to be a rock thrower, this should be something you expect, that every now and then somebody's going to show up and start throwing in your direction. You should show us how you're so skilled in navigating the rock field. All right, anyway. So that's the status of things. All right, so here we go. So this guy, Dino, says, just here to humbly request a short break from the double slit videos. Yeah, it's okay. I just mean that, you know, frankly, it's one of these moments in this whole thing. You know, I've had a few of them where, oh shit, sorry, it's not fixing. All right, where you know, the insight is so clear and it's such a good point. You know, like the lens is the wrong shape for gravitational lensing, and, you know, there's no possibility that an Einstein ring would be anything more than a sliver thick. Anyway, you know, little bits of stuff where you just say, well, they can't overcome that. I mean, they've got a huge problem and they won't deal with it. So I'm saying my new analysis of the double slits, the slit experiments, is just so decisive that it's almost like, well, why should I change the subject? We should beat this. You know, this is a good, whatever the proper metaphor. You're on a roll kind of thing. Keep the ball rolling. But anyway, I won't do that. Just for you. Okay, there are so many other interesting physics topics. Yeah, they all relate to the same thing, though. I mean, understanding what a photon is, once you understand its little quanta at a frequency, then you understand this whole idea that the field has places where there's more little lumps, more clumps, and there's places where there's less of them. And then that's the basic dynamic that allows for this push-pull thing to happen. Well, the pull is always just a push and drag. Anyway, there are so many other interesting physics topics to explore, and I'd love to hear how your theory applies to those as well. Well, I've done the 4 videos, the 4 gravity, you know, magnetism, light, and gravity, magnetism, light, and what the fuck's the other one? Well, anyway, I did them. Go watch them. They're in the whatever playlist, the subject one. Yeah, the 4 most recent videos in the subject playlist covers a lot of subjects. Anyway, again, I'm curious how your idea of gravity as pressure relates to what mainstream physics refers to as the quantum foam. Yeah, well, they refer to it as quantum foam, but it doesn't mean anything, right? Because quantum foam to them means that this stuff is going into the space and then popping out of the space. It annihilates, it regenerates. It's a, you know, you don't know what they mean. It's like when they say the word spin. Well, it's not really spinning. The annihilating isn't really annihilating. It's going into magic land, and then it pops back out of magic land in a new location, blah, blah. It's like there's a secret place in space where you go into the little black, you know, you could put a little black hole somewhere on the wall, and you can go into the hole, and then somebody can move the hole somewhere else, and you can pop out of it. I mean, it's cartoon mush. I mean, it might as well just be, you know, was it Bugs Bunny who had that little hole thing? Yeah, he could peel his hole off the ground and put it on a tree or something, you know. It's that bad. But, you know, you want to talk about it, okay. Phew. Anyway, and its apparent ability to move objects in the Casimir plate experiment. So this is there's 2 ways you can interpret all kinds of things, or 3 ways, or 5 ways, or 7 ways, and the interpretation of what's taking place in the Casimir effect, right? They just chose an interpretation that suits their silly theory. And it doesn't have anything to do with the reality of what we know about what these plates will do. So the idea is that if you take 2 neutral plates, okay, they're neutral, no pluses, no minuses, charges on them, they're the same charge, and you move them closer and closer together, there's a point where they become charged, and they become attractive, and they'll smash together, okay? So when you make it really, really close, when they're really, really close to each other, they'll smash together. Now, they already know the right theory, right? They know what's really going to happen is that the electrons are in balance on these surfaces, right? So the electrons are on the surfaces. Always the electrons are on the surface. Come on, let's get real, people. And it just depends on how close or far they are from their protons that decides what their charge is. So if they're really close to the proton, you could say they're positive. If they're very far from the proton, then they're negative. And so when you make something negative, you're just changing the proximity. I would say it's probably the other way around, actually. Okay, so if the electrons are far from the proton, right, then that would be a negative. I think, yeah. And if they're close to the proton, that would be a positive. It really doesn't matter, but it always matters. But I'm just saying, I can't do everything. Well, anyway. But the point would be is that the 2 forces are now equal, and that as it's pushed together, the electrons are going to have a tendency, okay, to not like this circumstance at all. This they will not like. Okay, electron on electron is not good news. And so, like magnets, the little atoms inside will flip. And it's like taking 2 magnets, equal magnets, that are on a little, they can spin like a compass needle. And you try to put them right next to each, 2 north ends pointing to each other. And it's basically going to be an argument about who flips first. And so whoever starts flipping, that is, going from expanded atoms to contracted atoms, whoever flips first, okay, sort of thing is going to happen. They're going to start flipping, and whatever side has more mass flipping, will end up going positive, and the other side will go negative. They already know this will happen. They already know this is the physical dynamic. Well, obviously, once one goes positive and once goes negative, obviously they would attract, okay, and that's why they would run into each other. Now, their silly theory, which might be in this video I'm going to play from Fermilab, okay, their silly theory, is that there's wavelengths trapped in here, right? Because everything's a frequency, and so their argument is when you get the plates too close to each other, the big frequency light can't fit in there no more, and so somehow I don't know what it does, right? It says I don't fit. What does it do? They don't have any evidence that the big frequency light sneaks out or something. So I don't know where exactly the energy goes. But they're thinking that because the light has a frequency, it can't bounce back and forth between here anymore. And so therefore the energy in here gets weaker, okay, because the big frequency energy can't stay in there. And so the frequencies from the outside world that have big frequencies and little frequencies and all kinds of frequencies, right? Which is sort of consistent with my theory in the sense that the pressure is coming from the outside. So they're conceding it's a push universe in a sense, right? And they're basically saying because there's less stuff in here and there's more stuff out here, the 2 plates smash into each other. And it's because you squeezed like all the infrared radiation out or some kind of crap like that. Somehow you squeezed the energy out. Silly answer, frankly, I think. Not much reason to believe. But they believe it because this fits with their frequency model. It works for that, blah, 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 blah. But it's not a good answer. So anyway, all right. So the point is a tiny bit of evidence gets turned into some kind of conclusive reason to believe some kind of mush. Something for which there can be lots of explanations. They decide we like this one. It suits our purpose, and we'll just forget that there's counter theories that are just as good at answering the question. Alright, so let us move on to this video here, I believe. Yes. So we have subatomic stories, the crazy world of quantum foam. He must have seen this video by Fermilab, and that's why he suggested that subject, I suppose. But this is such a bad video. There is so little explanation in here. It's all just rhetoric explaining how super fantastically fabulous it is. It's all so fucking fabulous. I mean, they really ought to defund Fermilab. It's just, you know, what the fuck? Loop-de-doo. These people are getting paid just to propagandize for a stupid, silly standard model.
Hi there, physics fans. In the last few episodes, we've talked about the particles and forces that make up the subatomic realm. But just what is it like to experience the world of the super tiny? A few movies have represented it, like the 2018 Marvel movie Ant-Man and the Wasp. But just what is it like? Sounds like a great topic for this episode of Subatomic Stories.
So he compares it to a frickin' comic book movie. Oh yeah, it's insightful physics. Ant-Man against whatever the fuck it was. Pile of Jello Man? Well, I don't know what it was. Ant-Man.
We've all heard just how weird the quantum world is.
People have heard all kinds of stuff and they don't pay any attention to it, though. I guess that's the problem. I don't know. You know, what was I going to do? Oh yeah, I was going to speed him up a little bit just because, yeah, who's got all this time to waste? Sorry, technical issue. I have to move. No, I can't move that. I have to move this out of the way. And then I have to do this and go to... Well, let's just speed him up a little bit just because, you know, we don't have all the time in the world here. Got to get something done.
We hear about such things as electrons simultaneously being waves and particles and objects not existing until someone looks at them. And that's all true.
Right. No, that's not all true. Okay? We hear that silly story about objects not being real until somebody looks at them. But that's not your physics, right? You don't believe that crap, do you? I mean, that's the crap for the, you know, people who turn your physics into silly crystal religions and shit. So you shouldn't be repeating that horse shit because, you know, there's no evidence for any of that crap that a consciousness needs to contemplate something because or it's not going to be able to know where it is. I mean, that's a pile of crap, and you know it. Nobel Prize winners say that's a pile of crap. So why are you endorsing crap stories?
Varying degrees. But I don't want to talk about these familiar features of the microcosm. Those features are all so 1930s and arise from when quantum mechanics was...
Yeah, well, whatever. So we don't want to talk about why you drew all these silly conclusions. And because if you did talk about it, you'd find out, well, it's because the guy said so and nobody filed an objection. So we let it stand because nobody complained. You know, he farted in the room and nobody complained. And so we said, okay, put the fart on the board. Counts.
First invented. Quantum mechanics explores the behavior of individual matter particles. Instead, I want to dive down to the very smallest scales and explore new features that were revealed in what is called the second quantum revolution, which occurred in the late 1940s.
Yeah, whatever that crap is. All right, so now they're blaming Feynman for all this stuff, which is funny because Feynman did all that stuff just as sort of hypotheticals. You know, technically this is what the math can do, so let's go ahead and play with it. Like one electron is in the universe and it just time travels to every place in the universe, and so there's only one electron doing everything. You know, some kind of wacky crap that everybody knows can't be true, just for fun, because the math is open-ended. You know, it leaves you the option to do silly things, and so you go ahead and do some silly things and waste people's time. So Richard was a fan of that because he liked doing stupid things that wasted time. But anyway, you know, it's... All right, so you're trying to separate. I mean, the good thing about Feynman was, look, he understood this clumpy thing. And so the clumpy thing is important. It was important to Feynman. Clumpy had to be somewhere in the story of what was going on because, yeah, it looks really clumpy. So the foam idea is you're just saying that if I go all the way, all the way to what's actually... See, this is just a simple thought experiment, right? You know that whole atoms just don't move, right? An atom is, even if you have this swirly notion of an atom, with this nucleus and all these little swirly bits and they're all spinning around and swirling around all kinds of whatever, orbits and all this shit. Even if you believe that, you sort of know that this thing doesn't go here unless this little bit goes here and this little bit goes here and this little bit goes here. The whole thing has to be pushed, but it's the little things that have to be pushed ultimately. There has to be a force that pulls on them or pushes on them. Now the pull idea, again, is just kind of silly, so you kind of know that, everything's just this, here's an electron in space. What does it do? Well, it's being bombarded by virtual photons, if you want to call them that, or gravitons, or whatever, Higgs bosons. Whatever the hell it's being, and it's interacting, and the interactions are telling it, okay, that there's more this way, okay, look, there's more of these things going over here, and so this is going to end up going here over time. And it'll do it in some herky-jerky fashion, because it's all a bunch of energy all the time, and so it's going to go, well, it'll go 2 steps forward, then 1 step back, and then 2 steps forward, and then 1, 2, 3 steps back, and then 6 steps forward. But over time, it'll end up going more this way than that way because more force interacted with it over here than force interacted with over here. So yeah, when you get really, really elemental, you know that these things don't move for magical reasons. They move because something forces them to move. And that's hardly... There's not much room for disagreement with that basic statement. That there has to be, even if you think these things are all projecting jello waves, you understand that the waves have to be hitting it. They has to be getting waves of jello here and waves of jello here, and the little pieces of the jello have to hit it, and it's like, look, you can look at the ocean and you really can understand as a person, you can understand it's not it's not goo. It's made of individual little water molecules, little clumps of water, and the clumps of water are sticking to each other and creating a tension. So if one goes someplace, the others have to drag along. They're stuck in drag. They're stuck dragging behind something like an airstream. There's the wind. Race cars do this drag thing, where they scoot in behind another car. The car's breaking the wind, zooming along, and another car sneaks up right in behind it, and is zooming along, and together they can go much faster than as individual cars. They get more out of their engines, especially this car. He's a big winner. All right, because he doesn't have to work as nearly as hard, and it's almost work for him to pull out of the drag. So once he's in the drag, the airflow is just so comfortable. And so obviously you could say that, once one water molecule goes this way, the other molecule has got to be sort of dragged along.
That's the era when Richard Feynman and others devised the mathematics that illustrates that not only that was matter quantized, but so were force fields. Instead of classical electromagnetism...
See, it'd be really great if they actually believed that, right? If they actually believed that the force, like the magnetism and all these other stuff, was little bits of energy that end up communicating between the object. Because then they could understand how simple the ping pong analogy is, that the paddles are the electrons, and then you have a ball stuck between them, and the closer the electrons get, the faster the ball vibrates between them, the more energy it imposes on them. So proximity, closeness, becomes energy. That's why matter, E equals mc squared. That's why mass equals energy, because mass equals matter being close. There, when it's close, there's going to be ping pong balls that ain't going to be very happy. Very excited. No, they're going to be the opposite. Very terrible. I mean, well, yeah, they're really excited, so I guess they have to be happy.
Which incorporates electric and magnetic fields Quantum electrodynamics, or QED, describes quantum forces as matter particles exchanging individual force-carrying particles.
Right. And so they think of it as force-carrying particles instead of force. So that's a key function that's just so funny. See, they say force-carrying because they haven't figured out a way to get around the pull thing. So they're still stuck with their silly pull idea, right? So instead of just saying something, look, I mean, I've explained it that if you just make two forces, you know, electron force and proton force, and then you have electrons and protons, and then you have an inverse reaction between those two. You know, the action being if this force hits this matter, it goes out perpendicularly, and if this force hits this matter, it goes out perpendicularly. But if this force hits this matter, it reflects, and if this force hits it, it reflects. So if you just have this 2 + 2 physics, you can explain push-pull. But anyway, you know, they have to screw the whole thing up, something that simple. They screw it up by doing this idiotic notion that there's an electron here and there's an electron here. And because they have to be able to say, well, if it's a proton, it has to attract it. And if it's an electron, okay, it has to repel it, okay? So this electron has to be able to do these two different things. Well, they can't do that by just shooting the force, right? Because that's not going to make the proton come to it. So instead they have to say, oh no, there's a force carrier, like some little thing, okay, I have a force in me. And when the force carrier gets here, it says, oh, you're a proton. Well, you have to go towards, okay? That's just the rule. The piece of paper says you move towards the electron. But if it hits an electron, the force carrier, well then it says, no, you don't like electrons, so you have to go away. You know, some kind of crap like that. So instead of just making it a force, you see, they just can't, the force carrier goes the speed of light to the object. If they make it have the momentum, then both protons and electrons would move away. And they can't have that happen. So they have to have an excuse why there's a pull force. And that's the only reason why they're doing it. So instead of understanding that, no, there's energy out here, and if you evacuate the energy here, that is, if you are communicating you know, the wrong color this way, you know, the wrong force, then the force all leaks out this way, and it leaks out this way, and that way you have a vacuum in between the proton and the electron. So yes, it'll still move at the speed of light. The vacuum, okay, the absence of a force would be communicated the same speed. Say if I take out this guy here, the absence of a force will be communicated at the same speed as the force. It's just that the absence is just that you've created less density of this force. And it's not less density, obviously, because it's still going to push an electron away. So obviously it's the force has a different effect. And because it has a different effect, it doesn't push the objects away. It instead creates a vacuum between. No ping pong balls reflecting. Ping pong ball reflects here, no reflection here. That's, you know, that's a simple solution. But see, they didn't think of that. So without that solution, they're stuck with this idea, how do I make a pull? And so that's why they have to call it a force carrier. It doesn't carry the force. Force is the force. The forces move at the speed of light, the speed of force. Again, a simple point. I mean, ask a physicist. Shouldn't it really be called the speed of a force? Because all the forces move at the speed of light. So shouldn't it be called the speed of force?
I explained the basic idea of this in episode 5.
Sure you do.
QED was the first theory that quantized forces, but the idea could be generalized, and it was applied to the strong force, which now is best described by a theory called quantum chromodynamics, or QCD, and the weak force, which doesn't have a particular.
So the strong force, they totally screwed up again. So simple, so frickin' simple. If you have a theory that actually works, right? If you have the right answer, it's really obvious what's happening. So the idea of the strong force is that the protons inside the nucleus are really close together. And there's no theory to justify that because they hate each other so frickin' much. I mean, it's pots and pans all day long with them, you know. I hate your fucking guts, you fucking succubus. And, you know, just, you know, throwing balonies at each other. They just hate each other. Well, anyway, And they can't explain that. They think of that as the strong force, because there has to be some incredibly strong force pushing these two things together, because there's no way they could ever be this close without some incredibly strong force pushing them together. Well, the simple solution is the neutron. So, boink, there, I created a neutron now. Now this one's a neutron. Okay, but it doesn't matter. I don't have to draw it like that. And what now can happen is all the electrons here, so all the proton energy, the electron force ends up leaking out the electron, right? And all the electron force ends up leaking out of the protons. So what do you end up with? Going perpendicularly. Instead of reflecting, it moves perpendicularly. So you lose all of the repulsive energy between the two protons, because it all gets deflected by the electron. And so now the protons can be a lot closer to each other, because there's a vacuum here and a vacuum here. So as far as the protons are concerned, all they're seeing is the electron, which they like. And so now they can be really close to each other. So you don't need a strong pressure out here. You don't need any strong force pushing them together, because there actually isn't any pressure between them anymore, because there's just one stinking little electron here to mitigate the whole problem. And the vice versa would work. You could put a proton in between two electrons, and you have the same effect. These electrons can get much closer because they don't see each other, so to speak. All the energy that would be reflecting between the two electrons, the ping pong ball, bouncing between the paddle, well, I can put a third paddle in that deflects the ball. And you can understand, well, no ball bouncing back and forth between the electrons anymore, so no problem. They can get much closer than they would be. Simple answer. Simple. No, we can't hear that. We can't pay attention to it. We can't even consider it. It's garbage. It's rubbish. Fuck you. Yeah. You're anti-science.
I made long-form videos about these, and the URLs are in the description.
Yes, and I've watched some of them. They're just too frickin' full of shit to be bothered with.
The term that describes these class of theories that quantize subatomic forces is quantum field theories, or QFTs. So, what consequences do quantum field theories have? Are they testable? How do we know that this crazy-sounding idea is real? There have been...
Yes, and he hasn't even gotten to the crazy-sounding idea yet. He thinks it's a crazy-sounding idea to say it's quantized. That's not very crazy. Right? The crazy part is when they start saying it pops in and out of existence. That's the crazy fucking part.
Several testable predictions of QFTs. Let me tell you about two of them. The first one involves predictions and measurements of the magnetic properties of charged subatomic particles with spin 1/2, like the charge...
Okay, so now we're stuck with this idiotic spin thing that isn't spin, this magical property that they gave every piece of matter in the universe, as if they all have to have their spin property. It's not a real thing. It's just complete bullshit. And the experiments they're using to decide its spin is polarization experiments. So most of the entanglement experiments involve polarizing light. They're experiments done on photons based on polarization, and they're calling that spin. I mean, what the hell is that?
Charged leptons and the quarks.
So now they're going to do a bunch of experiments on leptons. I mean, whatever. And the quarks. Well, the quarks you can't do any experiments on, so he's full of crap talking about doing experiments on quarks.
Precisely measuring the magnetic properties of quarks is hard, as they're buried inside protons and neutrons. But particles like electrons and muons are a different thing entirely. 1930s quantum mechanics makes a specific prediction of what is called the magnetic moment of a charged spin 1/2 particle.
So again, this prediction that they're saying the electron is a magnet, which there's no evidence it's a magnet. There's no evidence, there's no experiment that demonstrates that electrons are magnets, that they have a north and south side. There's only evidence that electrons are negatively charged. So they say they have experimental evidence, but you can't find the experimental evidence. Like I said, Stern-Gerlach is done on silver atoms. It's not done on electrons. There's nothing to do with this notion of testing the spin of an electron. This is all what they've told us happens in the part they can't see. So the part they can't see, they're saying something's happening. So when I would argue the atoms are merely changing their position, he's going to argue the electron is, moved its spin. I don't think they've disproven that other theories could be the right answer. They're just, again, quote mining the interpretation to say, well, look, our interpretation works. Well, yeah, lots of other interpretations will work too.
Cool. You can sort of think of the magnetic moment as the magnetic charge of the particle.
It doesn't. The magnetic charge. I mean, okay. Why would I hurt my brain playing that silly game? The dipole monopole.
When the magnetic moment of the electron was measured, it was discovered to be approximately 0.1% different from the...
Right, so this is nothing. When he says they measured it, it's like, oh yeah, they took a ruler out and measured it, right? So we have no citation to the experiment, so I'm going to have to look up this Polycarp Kirsch guy, I guess. Somebody write that down for me. Yeah, okay, I'll play the video again and write it down. We're going to have to find out what this frickin' experiment was that measured this tremendous accuracy of something called the magnetic moment of an electron. And I bet it's going to have nothing to do with an electron. It's going to have everything to do with measuring the magnetic moment of atoms.
Prediction of classical...
Which it just means the turning of the atom. The rearrangement of an atom.
Quantum mechanics. Beginning in 1947 and for several years after that, theoretical physicists applied the mathematics of QED to the problem to get an accurate understanding of what is going on near an electron or a muon.
Right, so they didn't do any experiments. They just did their little math stuff and started doing that whole, frequency equals momentum, and so momentum equals shoe size, and shoe size divided by hair fatness. Yeah, they're the same thing. Shoe size, hair fatness, same thing. Long fingers, long other things, Sure, it's the way it works.
The current thinking is that an electron is constantly emitting what are called virtual photons.
See, now that's correct. Everything is constantly emitting, right? So this is the thing that's the truth. Everything is constantly emitting. Everything. See, there's no zero temperature, because everything in the universe just has to, unfortunately, it's pretty much, you can't create a vessel strong enough to contain the pressure of the universe. So you can never create like a vessel and then evacuate all the energy from the vessel entirely, because the crushing force would be insane. Okay, so that's never going to happen. All you can do is make reductions, of course, and so you can create some thermal quietness. But the world of the electron is a world where he's constantly bombarded by just tons of this stuff coming from space all the time. These little pieces of photon, little pieces of shit energy, cell phones, all this stuff. It's constantly bombarding the electron, and all there is a summation. The electron calculates. It sits there saying, I'm getting hit. And it just says, how much am I getting hit by over there? How much is coming from over there? How much is coming from down there? How much? And it just goes wherever the weakness is. So if there's a weakness, an imbalance, it goes there. And what atoms do is they create a nice environment where the atom adjusts to the field. So when one electron moves, the other electron moves, and then this electron moves, and they all adjust to take care of any big imbalances. So when there's a whole little bunch of rain hitting this guy, he gets a little extra jolt. Well, everything gets a little extra jolt, and everything readjusts, because they're all sending forces here, and all those forces adjust. Okay, so when you make this electron closer, you push these electrons further away. They go a little bit further away, and there's a little less energy over here, and a little less energy over here, and this becomes positive, and this side becomes negative, and simple diagram of understanding everything's in this the universal field. Everything exists in the real universe. This is the real universe. Electrons, protons, neutrons. Neutrons are composite, so you shouldn't really count them. The elements are just, look, there's just the two kinds of force, the two kinds of matter, and the two kinds of interaction, and that's all there is. But the only universe there is the universe the electron is floating in. That's the universe. It's a little bubble in a bunch of BBs just getting bounced around. And it finds balance. and systems that create balance, and that's why it gets stuck. It attaches to those systems. So they're so close to the right answer, but this is what they had to do to the right answer, is create these fucking idiotic bullshit wavicles. Ugh.
Virtual photons are one that do not need to conserve energy momentum.
So, they're so desperate to make this work that they break one of the fundamental laws of physics, which is conservation. The idea that the photon is never destroyed. That the same photon, the one bouncing from even this camera, it's been here for billions of years. It's been bouncing around for billions of frickin' years. You can never destroy the energy. And here they're breaking their own sacred law of reasoning here. And, we're just going to make everything poofy now. It poofs away and then new stuff poofs out. The universe is just poofing the crap all over the place. Poof, poof, poof.
This is basically the Heisenberg uncertainty principle of classical quantum mechanics. These photons are then reabsorbed by the electron. Occasionally, the virtual photons can temporarily...
Obviously, they can, essentially, they're never absorbed, they just stick. The electron moves in a direction until another force acts on it. So the Newton rule of it goes where the force tells it to until another force tells it to go some fucking place else. And that's the rule. It just goes the direction it's going until something else says you can't go that way anymore.
Convert into virtual electron-positron pairs.
Oh, and then when they make up this nonsense, electron-positron pairs. I mean, let's go back to the invention of the positron, right? So a bunch of other guys do this experiment. They shoot cosmic rays through this lead plate or whatever, or radioactive material. They shoot the, the beta or whatever. And now and then, one of the protons does something a little funky, right? It's okay. So they just said, oh, it's a funky-ton. It's a proton acting weird. And then one guy says, I'm going to call that a positron. And so that's the guy who gets the Nobel Prize, right? The other guys already did the same experiment, came up with the same results. They just didn't call it a positron. They didn't say it's a new particle. They just said it's a proton that's a little bit fucking drunk. It had a hard time. Something happened to it. It was a little bit molested. It's a molestaton. Okay, so, it's missing its panties. Whatever. It wasn't that big a deal. And then all of a sudden they made it a big deal and had to give it a new name. But that's all they have for evidence. It's something that, could be a proton, but, it's moving too fast. So we'll say it has to be a positron. Just crap.
Then recoalesce into the virtual photons. Looking even more closely, those virtual electrons and positrons can emit their own virtual photons and so on.
So, looking more closely, look how really detailed it gets, all fun and blobby. Look, it's all Magiverse. Look, it looks like the real universe now. It's all pretty. Colors.
The result is a chaotic and complicated mess of virtual photons, electrons, positrons, and even other subatomic particles, all flickering in and out of existence.
Right. So he said it, not me. I mean, I can't slander him any better than he slanders himself. Poofing in and out of existence. Oh, please. That's the answer? That's the best you can do? Is this poofiverse bullshit? Oh, fuck.
In the vicinity of the actual bare electron.
So they don't, they have scant. I mean, the evidence for their conclusion is just paper tissue thin. It's nothing as evidence. Tiny grains, pieces of sand. I mean, it's nothing as evidence. And he talks like, oh yeah, we have so much evidence to believe this poofy woo.
The bare electron is enshrouded in a cloud of virtual particles flickering in.
He's saying it again. Flickering in and out of existence. La 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 la. Let's put it to music and build it out of gingerbread.
And out of existence. Now, this idea is kind of hard to believe.
No, it's impossible for a rational person to say, okay, I totally trust you. Totally. I mean, this is a Jesus story. It's a walking on water bullshit. He caught a fish and he fed 5 zillion people with it, blah, blah, blah. This is a fucking story. And you're not going to show me one shred of stinking evidence. Not a stinking blurry photograph, not a cigar like flying in space, nothing. You're going to show me nothing to give me any kind of reason why I should buy this wooey crap. You're just going to say, me and a bunch of other nerdy little fat eggheads came up with this bullshit, and we can sucker you fools. We'll write little signs on our shirts, and we're super nerds. It's just bullshit you made up.
But researchers have measured the magnetic properties.
Oh, yes, of course they have. Yes, again, with their magical measure the 1/10,000th of a proton ruler. That doesn't make any sense. So it's another question for you physicists out there. How the fuck can you measure 1/10,000th of a proton with a beam of light that you've crashed into a mirror 1,600 times? What are the odds that the surface of the mirror isn't perfectly flat? Yeah. What are the odds that some of the time the photon goes a little deeper and a little less deep and deeper and, many more times than the diameter of a proton length difference in your path, your light path? How can you measure with a ruler that varies thousands of atoms worth of distance something that is thousands of times smaller than an atom? Oh, that's right. It's theoretical nonsense.
Properties of electrons and muons to 12 digits of accuracy. And
oh, that's so impressive. They got 12 digits of accuracy for an experiment that's measuring really, they're measuring how long an elephant's tail is and saying, well, that's totally related. I'm telling you. You figure out how long the elephant's tail is, you know exactly how massive the electron is. That's how you do it. You want to know how heavy an electron is? Measure an elephant's tail.
theory can only make correct predictions if this virtual cloud is real.
They didn't make predictions about anything, so let's not play any games like they predicted anything until they saw it first. It's just the truth.
So that's strong.
Or it was so obvious that anybody could predict it, like an elephant sitting on a styrofoam cup. I predict it will crush the cup. Oh, aren't I brilliant?
Strong evidence that the theory is true.
Oh, please.
Perhaps even more interesting is a measurement of the magnetic properties of the muon, which is also precise to 12 digits of accuracy, but for which...
Oh, yeah, so it's another thing. They can't do that experiment anywhere in the real world, so they have to do that inside of one of their colliders, I guess, or their magical machines. So let's understand, every one of these machines that creates muons or electrons or anything, it's creating a bunch of other crap too at the same time. A bunch of other rays are shooting out of the instrument. And they can't tell what they're seeing. Oh, it's just so bad that people fall for this crap.
Which the theory and measurement disagree.
Oh, look at that here. All the way down at the 9th place, they start to disagree. Well.
That could mean that a new theory must be devised to account for the discrepancy. If the discrepancy is real, it could require a significant modification of the standard model of particle physics.
I think it would be silly to think that you can measure 9 places anything at those kind of distances. So, yeah. But who cares? The whole thing is stupid.
A new measurement of the magnetic properties of the muon is underway at Fermilab called the G-2 experiment. It's hard to make predictions, especially about the future, but they could announce the results of their measurements within a year.
So again, they don't even know what a muon is, so this is all just more horseshit. I would argue a muon is just an electron that's got a cosmic ray behind it. There's a ray pushing the electron until the ray runs out, because the electron's moving really fast, until the ray moves all the way through it, which takes time at the speed of light, right? The ray is moving the speed of light, the quanta in the ray, and the electron's moving near the speed of light, so it takes time for the ray to get through the electron. That's all a muon is.
It's one of the most anticipated measurements in modern physics. I made a long-form video about G-2, and the URL is in the description.
Yeah, I'm sure it's a video again with new content in it.
In quantum mechanics, electrons and photons are both particles and waves, but my description...
Well, whatever that means again, so more just this mushy crap that who falls for that? it's both things at the same time, or it decides to change into one and then the other, or what the hell are you talking about? The two things are fundamentally different. It's a brick and it's an ocean wave at the same time.
Description of the magnetic properties of electrons and muons use particle language. Have any experiments looked for the wave behavior of virtual particles, and is the idea of a cloud of virtual particles broader than describing the subatomic world close to charged particles?
Oh, who knows what that gibberish was? Close to charged particles, blah, 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 blah. So, was somebody impressed by that pile of mush?
Yes.
Ken Wheeler mush there. The hyperboloid transcends the, perturbation of the coaxial blah, 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 blah.
The cloud of virtual particles exists everywhere, even...
Oh, here we go again. The cloud of virtual particles, yes, no, they're not virtual. They are real. And they cause gravity, and they cause magnets to move, and they cause everything to happen. Everything that's moving that you see, matter, moving. It's moving because there's a force moving it. Little bits. Little BBs are hitting something.
In empty space, even inside you. At any spot in space, virtual quarks and leptons and photons...
Oh, virtual quarks and virtual leptons. So now they're virtual, too. And they're virtual because they can't account for them. So they're virtual in the sense they pop out of space spontaneously or something. I don't know. What does that even mean? Why do I have to even endure the unpleasantness of talking about virtual taxes? What? Virtual watermelons? What are you talking about? Virtual.
And all manners of subatomic particles are appearing and disappearing. The microcosm is a chaotic mess.
So I would argue it's clearly not chaotic. Chaos is just another bullshit human term. Like spontaneous, it's useless gibberish. There's no such thing. It's only a lack of ability to perceive. That's it. There's no chaos. Chaos is just, I can't fall. There's too many bouncing balls. Doesn't mean that I can do this literally. I can have some simple thing where each ball bounces exactly the same, and if I just make 6 or 7 balls bounce at the same time, you're like, oh, I'm confused as fuck. What's happening? But it can be incredible order in what's happening. No chaos at all.
There is a measurement that validates both the cloud of virtual particles in space and their wave nature, and it's called the Casimir effect.
Okay, so this is where, again, so I gave you the rational explanation for the Casimir effect, and here's the irrational one they came up with. So, sorry, but gee, it's just so obviously they have quote mined the interpretations. They've decided, oh, this is what we chose to blame it on, instead of saying, well, there are other rational theories for why the plates move towards each other. We're just not going to use those because they're not, they're not going to be conducive to us making this bullshit sound rational.
This experiment is conceptually simple. Take 2 metal plates and put them parallel to one another and separated by a very small gap. The virtual cloud exists both between the plates and outside. Now those virtual particles have all sorts of different wavelengths, big wavelengths, little wavelengths, medium wavelengths, the whole gamut. The key feature of the Casimir effect is that only the short wavelengths fit between the plates, while outside of them, all of the waves fit.
So, you heard it. That's their theory. Somehow the waves don't fit anymore, so the energy just doesn't exist anymore because it doesn't fit.
That means that there are more virtual particles outside than inside, and the net effect is those outside particles overpower the virtual particles in the gap, and the plates get pushed inward. And
there you go. They are pushed inward, that's a fact, but it's always a push. So he's got that part right, but this explanation is silly.
That's exactly what happens when you do the measurements. And of course, I've made
there's no waves in the measurement. There's no evidence of this exactly what happens when you do the experiment. The experiment, it just has a result. This is all your interpretation. This has nothing to do with what the experiment says. The experiment says nothing. You don't see a whole bunch of big radio waves popping out of the plates or something. There's no evidence of this inability of long wavelength energy to not be able to bounce back and forth, to have its wavelength changed, in fact, right? I mean, that's how energy is changed, is by this effect between electrons. You move the electrons further apart, you have a higher frequency if the energy escapes. If they're closer together, you have a faster frequency, longer wavelength, shorter wavelength. Not that complicated.
A longer form video that gives more details, and the URL is in the description. The idea that empty space isn't empty, but is rather a chaotic and ever-changing mess of virtual, quarks, leptons, photons, and all the rest, briefly winking in and out of existence, is a real mind-blower.
Oh, it's an extraordinary claim, and you have less than ordinary evidence, and that's my simple accusation. You're not even giving me any good reasons here at all to believe. You're just sitting here and saying, nerd told you so. I mean, it might as well be Moolah told me so. Funny guy with a beard sitting in the corner told me so. So why should I believe you? Well, I know mathematics. So what? That doesn't justify any of this woo.
But it's what the data says. It gives you a very...
There, so again, what the data says. No, the data says the two plates bang into each other. That's what the data says. All of this crap is what you made up as your explanation. I've given you another explanation that's perfectly consistent with the laws written by Maxwell, essentially. And I mean, the laws discovered by Ampere and Gauss and all of those guys. And those laws are all you need to explain why those two plates move into each other.
Different mental picture of the nature of space at the quantum level. You're going to be scratching your heads over this one for days. Okay, so... No, I'm going to just be contemplating how there's just no point. Just dig a hole and bury yourself, because this planet just is not going to do anything intelligent. That's all the time we have for today's episode. Let's see what kind of questions we have today.
So that's all he did on the subject. So half the video he just says, oh, the hell with the rest of the video. I mean, the hell with me actually explaining any of this crap with anything called credible evidence, or the hell with giving you any real reason to believe that has something to do with you understanding how we connected these dots, how we made this image of percolating universe out of the evidence. And they made it out of their imagination. They didn't make it out of any necessity, oh, the facts are so glaring. They didn't dig up a nice fossil. There's not a good fossil they can show you and say, look, it's evolution, for fuck's sake. It's so fucking obvious. No, they didn't do any of that. So, disappointing. That's all you can say. Just mush. I will, continue to attempt to plead with you to save your brain, okay? And stop listening to this crap and start using your brain to scrutinize it and ask, you've got to provide me better evidence than we did it. Gravitational waves. We did it with our 1/10,000th of a proton measuring device. Please. Alright, anyway. Yeah, that's enough. I surrender for the day. Move on. Try again later. Let's see if Baldy has anything new to say. Oh, we wouldn't have anything. I have to respond to what he said, which is, I don't know what the fuck he said. Yeah, I don't even know how to respond to it. Don't be bloody daft. I don't charge money for my time. Laughy face. I don't know what that means. It means he really wants $700 an hour? I don't know. What the fuck does that mean? Alright, anyway. Until the next time. This really shouldn't be this difficult. Just, making a counter argument should not be this difficult.